So the aldol reactions that we've taken a look at so far, the aldol is reacting with a molecule of itself. But what would happen if you added two different carbonyls to it, right? So if you added, for example, this aldehyde and this aldehyde, and you added sodium hydroxide if you wanted to do what's known as a crossed aldol. So it's an aldol reaction with two different substrates. And so this generally doesn't work out so well because you're going to have mixtures of things forming, right? So you've got this one and then you've got this one, right? Maybe the orange one turns into the enolate and then attacks itself. That's what you would get right there. Or maybe the one in purple turns into the enolate and then it attacks itself. That's the product you would get there. Or maybe the orange one turns into the enolate but then attacks the purple one as a carbonyl. That's what you would get there. Or maybe the purple one turns into the enolate and attacks the orange one. That's what you would get there. So in this case, you can see it's quite a mess. You've got 4 different products, and this is still a relatively simple reaction because in this case, we only have one alpha hydrogen. If we had an asymmetrical ketone, you would have even more diversity of products. So with the crossed aldol, it doesn't work too well, but there are ways we can fix this. We can use substrates that have no alpha protons. And so they won't be able to turn into the enolate. And so they'll only serve as the electrophile, and they'll be very reactive towards it. So an example of this would be formaldehyde, right? It has no alpha protons and it has no steric hindrance. So it's going to be very reactive as an electrophile. And then another example would be like benzaldehyde. Again, no alpha protons. And in this case, it'll form a conjugated enone, which will be very stable. And so that'll be your major product, right? So if you think about that, now we can do a crossed aldol with 2 different components. And now we don't have to worry about getting a whole mixture of different products because we can only have one component that acts as the enolate, right? So in this case, this one right here would act as the enolate, and then this would act as the electrophile and get attacked, and you'd be left with a single product. Same thing with the benzaldehyde. It would only act as the electrophile, and then your enolate or your other carbonyl would be what acts as the enolate. If we think about the product here, we would have this intermediate step with our addition product. But you can think about once this leaves and forms an alpha beta unsaturated aldehyde, we'll get a fully conjugated system right here. Right, and so it'll go straight to the product. You won't be able to isolate this aldol intermediate because the product is much more stable for it. And then even without heating, it'll go straight to the product. If we did want to do one of these types of reactions and we only wanted one of the products, there are ways we could do it. They're called directed aldol reactions. One of the books mentions it. The other book doesn't mention it. And I've looked at some online resources. Most of them don't mention it. So we're not going to go into detail there, but if that's something that you're interested in, you can check that out for yourself. But there are ways we can control it. Basically, it involves using a strong base and only one of your components at first to completely transform it to the enolate, and then slowly adding your electrophile to get attacked.